In this lecture, we will be talking about the psychometric properties of reliability and validity. These two properties are very important in terms of our assessment practices and our choice of testing instruments to use. As we've talked about, counselors have an ethical responsibility to select the best possible tests they can to obtain information they need to benefit the counseling process. In terms of best possible tests, we're looking for instruments that allow us to gather the information needed in a manner that is consistent with our needs, accurately represents the issues for which we are diagnosing the client, and does so in a manner that respects the client's rights and dignity. These two concepts, reliability and validity, provide us with the statistical or quantitative evidence that we need to determine whether or not a test is sufficient for our use, and also to compare that test to other instruments. It is these quantitative measures that allow us to determine whether or not the instrument we're using is suitable for the situation at hand. So let's talk about the first of these two properties, reliability. Reliability is the degree to which test scores can be viewed as accurate, consistent, and repeatable. The key word here is consistency. Reliability refers to consistency over time. People talk about wanting reliable transportation. What is it that they mean? They want transportation that they can depend on, that will function correctly time after time. When we look at consistency, we are looking at consistency across multiple administrations. So different times that I give the same test. We look at different people conducting the assessment. There should be reliability between when I assess a client, when you assess a client, and when another individual assesses a client. We could also look at reliability between similar but separate instruments. For example, there are several commercial instruments available to assess depression. The Beck Depression Inventory, Reynolds Depression Scale, Hamilton Depression Inventory. All of these can be compared. They assess the same construct, but are slightly different. We also could look at reliability or consistency when testing conditions vary. Was the test administered in the morning or in the afternoon? Early in the week or on Friday? Was a class offered online or on campus? So different conditions can also be assessed. Some important items to consider when discussing reliability. Reliability refers to scores, not tests. A test in and of itself is not reliable. In fact, it's not really anything. It's a piece of paper, or it's a computer screen with a bunch of words on it. Reliability relates to how we use those words or those questions or that instrument to derive scores. And it's the interpretations we make based on those scores that's deemed reliable. So using our depression example, if I give you the Beck depression inventory, that piece of paper with those 30 some odd questions has no real properties. It's the score we get. And that score, which tells me whether you are meeting criteria for depression or not, that I can evaluate whether it's reliable. If you are clinically depressed, your score on the Beck depression inventory should consistently, reliably reflect that. Whether I tested you today, tomorrow, a week from now, or if we had different people administer the test to you, you should have consistent results. So what affects reliability? Why do we not have perfect consistency all the time? Well, there's a lot of factors that need to be considered. We could look at changes, or mathematically what we would call measurement error. These measurement errors or changes will cause an individual's score to vary from test administration to test administration. Your score on a test is really just a snapshot picture of how you performed at that moment. It is not an absolute. In other words, it is not the definitive measure of your understanding or ability on that test. Things could change. Perhaps you're more motivated one day than the next to take the test. Maybe something happened the morning of that exam, positive or negative, that affected your mood and your concentration levels. Maybe the first time you guessed on some items. So there's always some difference, some variation in scores from administration to administration. Reliability then becomes a way to measure or assess how much change there is and how much of it can be controlled. There are some forms of error that we just can't control. Some things that cannot be systematically accounted for in our administration. A power outage in the building, for example, during the middle of the exam. An individual who woke up ill that morning and had an upset stomach during the exam. This concept of reliability is based on principles of classical test theory. Test theory assumes an equation, x equals t plus e. X is our observed raw score. For illustrative purposes, let's say that x is the score you would get on a quiz or exam. Your raw score could be 85. That's the score you got on your exam. That raw score or observed score is made up of two components, true score and error. True score is what you actually know. If we could somehow get to the core and tap into your absolute knowledge base that would be your true score. The E is the random error. It's all those other things that influence your score. So your score of 85, perhaps your true score is really 78. That means that the error component was 7, because 78 plus 7 equals 85. That was your observed score. Where did those 7 points come from? Those could have been questions that you guessed on and just happened to guess correctly. You did not necessarily know the information. You just benefited from random luck or good selection on your part. Reliability estimate that we compute, this value that we're going to be talking about, is going to represent a proportion. A proportion of true variance and error variance. True variance is variance that we would expect to occur. Nothing is really precise 100% of the time. There are always some variations. That's why we usually give estimates in confidence intervals. If you watch the weather report, they usually give you a range of what the weather is going to look like, or a percentage of the likelihood that it will be storming or raining. So we know that scores will vary. And we're trying to determine how much of that variance is related to some type of measurement error, whether it be something with the administration of the test, the construction of the test, or the mindset of the individual going into the test. And we try to separate the two. The less error variance we have, and the more true variance, the greater the reliability of the test. And so you should note that this relationship stipulates that we want to have true variance. That is a desirable characteristic. There should be differences between scores and individuals. The whole point we assess or measure people is to categorize. We give a depression inventory because we want to see if an individual meets criteria for depression or not. If everybody scored the same, then the test would be meaningless. It would neither tell us whether you were depressed or not, because everybody got the same score. In similar fashion, if an instructor gave an exam and everyone got 100, the exam really had no point. It did not differentiate between people who knew the material and who were unable to demonstrate knowledge of the material. So we could look at an example. Say we have a student, Johnny, who has taken the SAT test, and he scores an 870. He retakes the following semester and scores a 1040. And so the SAT is going to be used in his college application process, and he gets much better the second time. What is the difference in his scores? Well, on face value, it's a 170-point difference. The difference between 1040 and 870 is 170 points. What caused the difference? Well, it could be any number of things. Maybe Johnny studied more the second time. Perhaps he bought study materials, enrolled in a course or a workshop, hired a tutor. Maybe he got a better night's sleep before the exam, was more prepared. Perhaps the second time around, now he was familiar with the format of the test and less bothered by not knowing what to expect. The causes of these errors is what we're trying to assess. How much of it is really knowledge gained on Johnny's part, and how much of it was some of these other items, where he took the test, when he took the test, whether he slept the night before. And we want the error variance to be small. You'll note here on the slides that I ask a question, is that correct? Sometimes we don't want error variance to be small. Let's look at some applications here. This error that we've been talking about can be described in two different ways: systematic and unsystematic error. Systematic error occurs when a test is used and it consistently measures something other than the trait it was designed to assess. Students in mathematics courses will sometimes complain that they have difficulty with word problems. It may be that they have the math ability to perform the calculations, but they have difficulty figuring out what information they have and what they need to do when reading a word problem. I could give an exam in a math class that consists of all word problems. It could, however, be the case, though, that the differences in scores really reflect students' ability to comprehend what they read in word problems more so than it does mathematical ability. In other words, the students who scored lower, their lowered scores could really be more related to their reading capabilities than their mathematical capabilities. Unsystematic error is a collection of random error that comes from sources that we note either about the administration of the test or the test itself that we really can't control. Perhaps the instrument was normed or designed on a sample of students from the Northwest United States, and we're using it in a Southeastern school. Perhaps it's a computer-based test, but the computers at our school or facility are older computers, and it takes longer to load the questions, and the computer freezes up several times. These are all sources of error that we could note, but not necessarily control. You could take all these unsystematic errors and put them into different categories, subcategories, if you will. There are time sampling related errors. This has to deal with when the different versions of the test or the different administrations of the test occur. Time sampling effects, you may look at carryover effect. An individual, if you assess them too quickly, they may just be recalling the information from the first administration and not really learning the material. If I tell you that the capital of California is Sacramento, and then I just ask you now, what is the capital of California? You would answer Sacramento. Did you necessarily learn that information, or did you just remember it from a mere moment ago? There also could be practice effect. Once you're familiar with the test, you typically are able to perform a little bit better. And finally, fatigue. Multiple administrations, test takers may get fatigued and tired. Their performance may suffer or diminish. We also could look at sampling related error. Perhaps the items on the test itself are not indicative of what we really need to be measuring. If I were to give you a bunch of questions on an exam in this class that dealt with automotive repair, we're sampling from a content set that's not really related to the practice of counseling and assessment. There could be test administration errors. Different individuals administering the test, different testing conditions set up. Maybe it was in a different classroom. The lighting was different. The temperature was different. And then finally, we could look at test taker variables, characteristics about the individual that may have altered scores or changed scores. And we talked about motivation, whether you got a good night's sleep before, concentration, things such as that. So several different sources of error that we need to account for. Taking all of that into consideration, we can look at ways of calculating reliability or assessing the consistency of test scores. Measures are deemed reliable when individual scores remain nearly the same on several repeated measures. So they don't have to be exactly the same, but they should be similar. A clinically depressed individual should roughly have scores on a depression inventory that indicate depression. If one day they take the test and they are severely depressed, and the following week they take the test again and they show no signs of depression, it's probably not very reliable. When we look at calculating consistency, the correlation method is what we use. Correlation is a measure of relationship. How related are two different variables? In this situation, we are correlating true variance and error variance. The result is a statistic known as the correlation coefficient. And this is what you typically see reported in research, in test reviews, and product information. The correlation coefficient varies. There is a range, however, that restricts what this value can be. Coefficients will always fall between a range of -1 and +1. These two extremes, the -1 and the +1, are considered poles. They are polar opposites of one another. A positive correlation indicates that scores on different measures are trending in the same direction, either both going up, which is positive, or both going down, which is negative. A negative correlation exists when scores go in opposite directions. On one administration, the scores go up. On another, the scores go down. The closer your computed value is to these poles, the stronger the correlation. A score of 0.95 is very strong. It is very close to 1.0. A score of 0.36 is not as strong. It's much further away from 1.0. Scores that are in the middle, so a reliability coefficient of 0, are indicative of no consistency whatsoever. We cannot make any accurate statements about how reliable or consistent these measures are. There are many ways to measure correlation and several different reliability coefficients that you could compute. The most common is the Pearson product moment correlation. Though you're not required to do the math and solve these in this course, I did want to show you how these reliability coefficients are computed. So here on the slide you see the formula for the Pearson product moment correlation. And it is a ratio. A ratio of the combined variance to a ratio of the variance for each item individually. At the top, you see the sum of x times y. So we have two different variables, x and y. X is your score on the first administration of a test. Y is your score on a second administration of a test. On the bottom, we have the individual correlations. How everyone did on test X and how everyone did on test Y. So if we had a set of scores, 7 different individuals, each take 2 different measures. Let's say the test the first time, their X score, and the test Y when they take it a second time. From first glance, looking at this table, you'll see that there is variation in the scores. How much variation? And what does that tell us? Well, we can compute. Using the formula, we square each of the X scores, square each of the Y scores, and then we determine a product of X times Y. And on the bottom, you'll see the totals, 300, 336, and 281. We can plug those into the formula for the Pearson product moment equation, and we end up computing a value of 0.89. From that, we could discern a couple of things. One, it's a positive value. That means that we have a positive correlation. Scores on both tests seem to go in the positive direction. In this case, it looks like they both go up from administration 1 to administration 2. Second, we look at the number itself, 0.89. It's a pretty high number. Remember, 1.0 is the highest we can go. So we could mean that this was a fairly reliable test score. Calculating these Pearson product moment correlations can be done for several different types of reliability. The 4 primary types of reliability you see in research and assessment reporting are test-retest, alternate forms, internal consistency, and inter-rater reliability. These could be computed both for formal measures, standardized tests, or for other types of assessment approaches as well. Our discussion will focus mainly on using it in testing situations. So let's look at the first, test-retest reliability. This is a measure of the relationship between scores on separate administrations of a test given to the same individual. So if I were to give you a quiz on this material, and then 2 weeks later give you the same exact quiz on the same exact material, I could then compare or correlate your scores on those 2 measures. When using retest format, the interval that you use between administrations is important. The longer you wait the less reliability you have. If I give you a quiz on this material, and then I give you that same quiz 2 years from now, a lot could have happened, and a lot of that information may have escaped your memory. Shorter intervals may, in fact, be assessing more practice and memory than it is actual learning. So the Sacramento, California example. If I assess you again very quickly, it could be that you just remembered the answer. The decision of whether to use a longer or shorter interval will depend on the construct you're assessing. Would you expect there to be change happening rapidly, or would it be something that would have to take place over some period of time? A second type of reliability is alternate forms. Alternate forms reliability is when we compare scores on separate but equivalent forms of the same test. So for example, perhaps I had a large test bank of questions. And for this chapter, I had 100 different questions. I could create multiple versions of an exam, 10-question exam, from this test bank. The questions all are equivalent. They're assessing the same concept, reliability and validity. But the question exams are different. They have different questions. I could give you both and see how you compare. The challenge with using this approach, however, is coming up with enough items to construct multiple versions. Sometimes it's challenging to come up with enough items to create one instrument, much less multiple versions. A third type is internal consistency reliability. This is a measure of how intercorrelated test items are to one another. On a test, items should have a relationship to one another. Simply because they're all measuring the same construct. On an intelligence test, all the items should be assessing some aspect of intelligence. So we would expect those questions to somewhat be related to one another. We do, however, want to balance this out. If items are too highly correlated to one another, it could be that they're assessing the exact same thing, and thus there's overlap. There may not need to be both questions on an exam. If on a second grade math test there's a question 2 plus 3, and then later on the exam there's a question 3 plus 2, they both measure the same concept. Can you put these two numbers together for a total? And we may not need both of them. It's this type of reliability that research look at to determine what items should be on a test. The items you see on a test are usually the result of an extensive analysis that is pared down an initially much larger set into the set that you see. There are several ways that we could look at measuring internal consistency. The most basic and common approach is the split half reliability approach. It involves taking the test and dividing it in half into two comparable halves. So if I give you a 100-question exam, after the exam I could divide it up into two 50-question sections and compare how you did on section 1 to section 2. The key here is to make sure that the test is comparable. Items on one section should be similar to items on the other. In cases where material is presented progressively with easier questions at the beginning and they get harder as they go, it wouldn't make sense to divide the test first 50 questions and second 50 questions, because the second 50 would be much harder in content and difficulty rating. Therefore, when using the internal consistency split half method, it's best to divide the instrument in half by odds and evens. This way there's an equal representation or balance of easier, mid-level, and challenging questions. The concern with using the split half approach is in sample sizes. Depending on the variables being assessed, you may need a much larger size test to be able to accurately divide it into separate sections. You could compute split half reliability by looking at the Spearman-Brown prophecy formula. And it's basically an extension of the Pearson product moment correlation coefficient formula that we looked at. What it does is it adjusts for the fact that these two versions now are, in essence, really just condensed halves or sections of one larger instrument. Once we compute a reliability coefficient, we can then plug it into the Spearman-Brown prophecy formula. The formula reads to take 2 times the reliability coefficient we compute and then divide it by 1 plus that same reliability coefficient value. An alternate approach is to use something called the Cooter-Richardson methods. And there is a Cooter-Richardson, or KR20, and KR21. What this approach allows you to do is make comparisons between specific items on a test. If I were to give you a quiz on reliability, and let's say I had 3 questions that specifically talked about internal consistency, I could then compare your scores on those items to see if there is consistency in your knowledge of consistency. There is a computer-based program that will help you in determining KR20 or KR21 values. The reason for the 2 instruments is to take into account item difficulty. The KR20 is used when item difficulties are not equal. In other words, some questions are easier than others. When all the questions are the same in terms of difficulty, the KR21 is used. Again, we're not going to get too much into the calculations, but I formulas that you'll see. The third approach is the Cronbach alpha method. The Cronbach alpha method is used when you have no right or wrong answers on a test. It's like rating scales that have versions from strongly agree, somewhat disagree, strongly disagree. There's not necessarily a right or wrong answer to either of these. And so this approach, this formula, is used to construct reliability coefficients on that type of data. The fourth type of reliability is inter-rater reliability. This is used when we want to compare level of agreement between 2 or more raters. So in beauty pageants or in Olympics where there are judges, each judge gives a score. At the end of the day, we can then compare and correlate those judges' scores to see how consistent they are. The best way to do this is to examine scores from each rater and then compare them. So we would look item by item and take the number of agreements where individuals scored it the same and divide it by the number of times that there was disagreement. The resulting ratio serves as our inter-rater reliability estimate. A concept that's related to reliability is standard error of measurement. Standard error of measurement, or SEM, as it's often abbreviated, refers to the variability in our set of data. It's a measure of how dispersed or how condensed the scores in our distribution or our test are. It assumes that the standard deviations of a normal distribution are the same for all persons in the group being evaluated. You typically see SEMs listed in assessment reports or educational reports. The smaller the value, the more reliable the measure. The larger the SEM, the less consistent or less reliable the measure. How could you increase your reliability and better your estimates? Well, you can increase the length of the test. The more you have, the more data you collect, the more reliable your results. You also could increase the heterogeneity of the norm group. Get a norm group that is diverse, that incorporates all the different characteristics or demographics of the population from which you're assessing. You also could utilize optimal time intervals between the administrations of the test, selecting an interval that neither causes an individual to just rely on memory, nor is too long that they've forgotten what they learned. The most common approach you see is 2-week intervals. The second concept we talk about is validity. Whereas reliability talks about consistency, validity refers to how well a test measures what it claims to measure. In other words, validity is a measure of accuracy. Of the two, reliability and validity, validity is the number one factor you should consider making a test selection. Validity is more important than reliability. And I'll give you an example. In a history class, I want to assess your grade in history, and I give you a calculus exam. And everyone scores poorly and fails. 2 weeks later, I give the same exam, calculus exam in the history class, and everyone scores poorly and fails. These scores are very reliable, they're very consistent. Students keep failing, but it's not very accurate. Calculus does not assess how much you know about history. So we could have tests that are poor, but we keep getting consistent results. That doesn't mean they should be used, however. So validity is more important than reliability. Like we talked about with reliability, validity is not a characteristic of the test itself. It's your usage of it, how you use it, how the scores will be applied. There are different types of validity that you can assess. Neither of these are better than the other, but the three major ones we talk about are content, criterion, and construct validity. The first of these is content validity. In content validity, we're talking about the items on the test represent a defined universe or content domain. And the items on the test should represent content domains proportionally. So let's say that I am that history teacher, and we're going to exam on World War II. That is our content domain, World War II, that event, that period in history. Items should be selected that represent that content domain or that construct. So questions on the test should all relate to World War II. We should not see any that relate to before the war, after the war. If this is an exam that covers multiple chapters in a book, the questions should be proportional to the amount of time placed on those chapters. If several weeks are devoted to chapters 1, 2, 3, and chapter 4 is covered in less than one class period, the majority of questions on the test should not be from chapter 4. The challenge with content validity at times becomes selecting a construct. Intelligence, for example. What does intelligence entail? Coming up with a content domain is challenging. Is it all intellectual? Is there emotional intelligence? Is there hand-eye coordination, object manipulation? So coming up with a content domain can be challenging. Typically, we have experts in the field review what we came up with. They give you insight of whether you have oversampled a certain construct, undersampled another, or potentially give you ideas, questions that you should include. Sometimes you'll see the term face validity used. People assume it's content validity, but it's really not. There is no scientific basis to face validity. Face validity means looking at a test, and does it look like what you think it would be? A math test, you would expect to look at it and see numbers. It has face valid, but it may not be content valid. Maybe it's a statistics course, but all the questions were on geometry. A way that content validity can be measured is by using the content validity ratio. This ratio is made up by looking at the number of individuals who rated the item and the number of individuals who thought that it was an essential component of that construct that you're measuring. So we have the individuals who rated it and the number of those individuals who thought that it was important. When more people think it's not important than those who think it do, It's probably an item that's not essential and does not need to be on the instrument. A second type of validity is criterion-related validity. With criterion-related validity, instruments are systematically related to an outcome criterion or an external variable. Here we're looking at your performance and how well it predicts a criterion. The SAT, the ACT, GRE tests of that nature are trying to predict performance on a criterion, how you perform in college or graduate school. There are two different types of criterion testing we could look at: concurrent and predictive. Concurrent validity looks at real-time performance. Predictive validity looks at future performance. An example of concurrent validity is scores on an exam and performance in class. A student may have an A average in class, they take an exam, and they get an A on the exam. There's high concurrent validity. Predictive validity are scores in classes in your counseling program, and then your score on a comprehensive exam at the end of your program. Students who do poorly in classes during the program end up not passing the comprehensive exam. An example of strong predictive validity. When selecting criterion, there are a couple of items you should look for. Criterion should be relevant and useful. There should be a rationale for why they were determined and how they help our understanding of a concept or a client. They should be reliable, consistent from situation to situation, individual to individual. They should be free from bias. There should not be any external influence on the criterion. And finally, they should be immune from contamination. There should be no systematic error in determining these criterion. So we can set a criterion for a school that a student needs a 70 or above to pass. Well, we want that criterion to be relevant and useful. So why did we determine 70? What's our basis for having 70? It needs to be reliable. 70 needs to be the passing score for all students. It needs to be free from bias. There are no issues where teachers may rate individuals differently because of biases they may have. A teacher may like a student more or find a challenging student more difficult to work with. And that criterion should be immune from contamination. The curriculum, the courses, the instructors should be consistent so that that criterion of a 70 passing score is relevant to all students. The third type of validity is construct validity. Does the instrument measure a theoretical or hypothetical construct? It deals with the question, what do scores on this test mean? Constructs, by their very nature, are abstract entities. They can't be directly assessed or valued because we can't see them, we can't touch them. And so since they can't be measured directly, we have to come up with alternate ways of measuring them. Intelligence, for example. We cannot see intelligence. We cannot hold it. And so we have to come up with alternate ways of measuring it. Two different types of construct validity are convergent and discriminant validity. Convergent validity is when an instrument is related to other variables it should theoretically be related to. An example is a math test in a math class. Students who are getting A's in the math class should be doing well on the math tests. We would expect there to be a positive relationship. Discriminant validity is when instruments are not correlated with variables in which they should differ. So if we're assessing math ability, math test, that math test should not correlate with how you're doing in your social studies class. We would not expect them to have any relationship between the two. They would be discriminant. There are several ways that we can gather construct evidence. We could correlate our tests with other tests. We can correlate with relevant data we find in the research. We could assess the uniqueness of our test. Are we measuring a construct that may not have been covered in previous instruments? We could compare our results to other groups that may be diverse, different populations. All of these approaches use a mathematical concept known as factor analysis. And factor analysis allows us to determine whether or not the items we have actually do correlate together and make up evidence of a construct. So now that we've talked about measures of reliability and validity, let's briefly talk about how these do the actual inclusion of items on a test or measure. Items are included on a test after they go through a period of item analysis. Researchers come up with several potential items for a test, and those items go through an analytic process in which they are examined and assessed. Different versions of the test are created, and the strongest one emerges as what you see as the final version. There are different methods you could look at to do an item analysis, and we will look at two of them briefly. The first is item difficulty. This is a way to assess how difficult items on a test are. Is an item too easy? Is it too difficult? Ideally, we want items that are right in the middle. To calculate item difficulty, we create a proportion. The number of people getting it correct, that item correct, to the total number of people who take the test. This proportion could range between 0 and 1. The optimal difficulty we want is 0.5, right in the middle. Why would that be? Well, if it's 0.0, that means everybody got the item correct. Nobody got it correct. If nobody's getting it, then it's not a good item. It's obviously not assessing something that was on the content list. It wasn't covered in the course. If the difficulty level is 1, that means everybody's getting it correct. It does not differentiate who was a better student or who was a less prepared student. If everyone gets it correct, it doesn't tell us anything to differentiate these students. So our optimal item difficulty is right in the middle, 0.50. A second approach is item discrimination. This is where we look at how items differentiate among different groups of people on the test. We typically divide the test takers up into groups. The high scoring, top 25%, the lower scoring, or the lower 25%, and we see how they performed on individual items. Items that are endorsed by the top test takers as correct are included. If there's an item and only the top people got it correct, it's a good item. It differentiates people who know the material and who do not. If there's an item that all the lower scoring people got that one question right, but all the top scorers got that question wrong, then there may be a problem with the item, and it may need to be re-examined. So these are approaches that researchers use in determining items. As you choose instruments based on your newfound knowledge of these concepts, keep in mind some characteristics. Tests can never be more valid than they can reliable. Validity by nature is going to be less than reliability. It's easier to get consistency. It's much harder to accurately assess constructs that are theoretical in nature. Consider the size and makeup of the samples used in the reliability and the validity studies. As you review the research or look through the test manual for tests you intend to use, look at the samples on which they created the instrument. Are they large enough to give you sufficient data to make your decision? Is the sample consistent or similar to the people you're working with? Some guidelines to help you interpret reliability and validity. And these are not etched in stone, these are just rules of thumb. When interpreting reliability, 0.8 or higher is good. 0.9 and above is great. 0.5 to 0.79 is okay. And anything below 0.5 is considered weak. Now, if we come over to validity, you see that anything above 0.5 is considered very good. Between 0.25 and 0.49 is okay. And below 0.24 is weak. So the scales for determining sufficient use are different for reliability and validity. And as we said before, validity is never going to be higher than reliability. And as we conclude, there are some other considerations that you need to account for when selecting tests, in addition to the reliability and validity of the test. These include the time of the testing. When will you be doing testing? How long does the test take? How much does it cost? What's the format? Is it multiple choice? Likert scale response? What's the readability level? Is it appropriate for my age group? The ease of administration, as well as the ease of scoring and interpretation. Keep in mind that tests need to be appropriate for the clients with whom we work. So consider your clients, their age, ability level, the need that you have in terms of information that you need to gather, and then select the best possible option. Choosing an instrument that has psychometrically sound properties, reliability and validity, as well as practical validity and usability. In doing so, you will be selecting instruments appropriately for your clients.